So this is the Intermediate Algebra 2nd edition on the OpenStax website. So if you would like to follow along with your own, this is the source. So this section, as you can see by the title, is about evaluating and graphing exponential functions. In this section, there are three main objectives. We're going to graph exponential functions, we're going to solve exponential equations, and we're going to use the exponential models discussed in this section in applications. Okay. This first stuff, as you are likely familiar since you've been using this book already, these are just to make sure you're ready for this section. So you should try these problems out. Maybe pause this video right now and try them, and go on to OpenStax and check your answer. Okay. If you feel confident in those, then you can continue. Because if you're not feeling confident in these, it's going to be hard to understand what's coming next. So moving on. In order to graph exponential functions, we need to know what they are. So we can see here the definition of an exponential function is it's a function. It's going to have this value right here. This a is called the base. Okay. That base needs to be positive, so that's the a is greater than 0 part here. And that base should not be 1. Okay. Other than that, that's our function. It's just f of x equals our base a raised to the x power. So before we continue, let's talk about why a should be positive and why a should not be 1. They mention that a little bit in the book here. So if you've done the reading, you likely already know what's about to come, but let's talk about this. So we have f of x equals a to the x. Okay. So the reason we want a to be positive is twofold. Okay. First, we want a to not be negative. Second, we want a to not be 0. Okay, to be not negative and not 0 means it's going to be positive. And then we also have the a is not equal to 1. So let's see why each of these is important. Okay, starting with this one here. A should not be negative because we want the function, in this case called f, to be continuous. We don't want it to have any gaps in it. So we want f to be continuous. Okay. Let's see why it would not be continuous if we had a was negative. So let's say a is negative. Let's just make it pretty simple. Let's make it -4. Okay, nothing too extreme here. So that means we have f of x equals -4 to the x power. So let's see what would happen if we tried f of, let's say, how about 1/2? Okay. One of the things we know about exponents is if the exponent is a unit fraction, and I should say a positive unit fraction, what this means is you're going to be taking a radical. So in this case, it would mean taking the radical of -4, and it's just the regular square radical, not some other index. Well, this is not a real number. It's an imaginary number. In particular, if you've learned about imaginary numbers, this would be 2i, where I is the imaginary unit. And if you're talking about a function, f, where your inputs are real numbers and you want your outputs to be real numbers, which in an algebra class, that's typically what you want, then that would mean that we are going to have a gap right there, right? It's f of x is, in this case, f of -4, is not going to be a real number. So that's not going to exist. That means we have to take 1/2 out of the domain, for example. And then there's various other things that are not real numbers. But let's look at one that is. You might be thinking, okay, well, it maybe it just means that you have to restrict the domain to, say, whole numbers or something like that. Well, if you're restricting it to whole numbers, then it's already not a continuous function, because you're going to have gaps between the whole numbers. And then you might think, well, okay, maybe I just throw out a few, okay? Because something like f of -3, that exists, okay? In this case, it's an irrational number, but it's still real. If you want to punch it in a calculator, you'll get a real number here. It'll be -1 point something or other. Off the top of my head, I don't know it, and it's not really worth getting out a calculator right now. So this one is not defined, okay? But let's say we try 1/4. This is again going to be imaginary. In particular, it's actually the radical of 2i. And you'll learn about in a future class, depending on which class you take, I guess, how you could actually calculate that radical. But the point is it's still going to be imaginary. It's not going to be a real number. So you end up with kind of alternating, even if you just stick with the unit fractions here, you'll end up alternating between not real, real, not real, real, and so on. And so that's not even getting particularly nasty with our inputs, right? So this is just a long-winded way of saying, since we want f to be continuous, we don't want negative values for our base. Okay, just a reminder, that value right there is the base. Said that earlier, but I never wrote it down, so let's get that on there. Okay, so now the question becomes, well, why do we want a to not be 0? And why do we want a to not be 1? Well, these two come from the fact that we want f to not be a constant function. If we're going to call it an exponential function, it should be different from previous types of functions we've already dealt with. It's okay sometimes for a function to be more than one type. For example, a linear function is also a polynomial function. Something like f of x equals x squared is a polynomial function and a quadratic function and a power function, etc. But in general, you don't want to include constant functions in many types of those. So let's see what happens if a were 0 or 1. Okay, so let's say we have a equals 0. Then that would mean that f of x equals 0 to the x. And if you plug in anything other than 0 for x, you're going to get either 0 or something undefined. If you plug in 0, technically it's still undefined, but as you approach that, weird things happen. Okay, but essentially what you have is this thing will be 0 if x is positive. Let's see that. We have 0, say, to the second power. This would be 0 times 0, which is 0. If we had, say, 0 to the 1/5 power, well, that would be the 5th root of 0, which is 0. Okay, you raise 0 to any positive number, you're going to get 0. Okay. If you have either 0 for x or a negative number, then you're going to get something undefined. Let's see a few of those examples. So let's say I tried to find 0 to the 0 power. Like I said, that one is kind of funky. As you approach it from the right, if you plug in smaller and smaller and smaller numbers for x, like you start with x is 2, x is 1/5, and then maybe try x is 1/100 or something, it's going to be zeros, which makes you think this might be 0. But if you plug in negative numbers, like say -1, that would be 1/0, and that's undefined. And even if you plug in something really close to 0, like say negative 1 over 1,000, that would be 1 over the 1,000th root, I should say radical, of 0. Well, that's 0 again, so we would have 1 over 0, which is undefined. Okay, so if you plug in numbers closer and closer to 0 from the negative side, they're all undefined. So that makes you think, oh wait, no, this is undefined. Okay, since you can't really say which one it is, we say that it's approaching an indeterminate value, but since there is no value it equals, we still say it's undefined. Okay, so what this means is we end up with, if a is 0, we have f of x equals 0 to the x power, and this thing is not even defined for x equals 0 or negative values, and when it is defined, it's always 0. So that means it's a constant function with a limited domain. Okay, so that's 0. Let's look at 1. This one is a little bit easier to deal with because literally everything in here, no matter what you plug in for x, you'll get 1 for the output. 1 raised to any power is 1. So this would most definitely be a constant function. And since we don't want it to be a constant function, those don't really feel like something that needs to be included in the exponential functions. We don't allow that base. So again, this is just emphasizing the fact that exponential functions look like this, where the base is positive and not equal to 1.